Hello everyone. Hello. Hey Alice. Hey Karthik. Manish. Hey Muskan. Hey Muthu. Hey Rajesh. Hello everyone. How all are you doing? I hope you could get some practice with Seaborn in the last class, and I also believe that it made your assignment easier, your Netflix use cases easier. Just wanted to do one quick check. Am I audible? Is my voice clear? Cool, perfect. Loud and clear. All right, great. So let's wait for another 2 minutes and maybe we can get started. Let's wait for other folks to join. Hey Manish, hey Aditya. How's the Netflix use case practice going on? When is the deadline? When is the deadline? Tomorrow? All right. Tomorrow what? 12, after 14 hours. All right. Haven't started it yet. Aditya, back up, man. I think most likely, I think tonight they'll also upload one more case study, or most likely, if not today, Monday night, Monday evening. So yeah, try to wrap up all the work that you have. Prioritize submitting these business use cases. That's the most important part. Tomorrow morning. Okay. So probably 12, 12 noon is the deadline, if I'm not wrong. All right. Decoding ratings became difficult as they were encoded. Um, okay. So I think probably Suraj will also take a business use case, and I'll ask your doubts and still probably submit after that discussion with a slight bit of penalty. On an average, how many insights do we need to do? I think there's no number as such, and if there is some number that they're expecting, so I guess it should be 4 or 5. But even if you have like two strong insights, which are meaningful, I think that's enough. I mean, it's about the quality net, not the quantity really. But yeah, I think 2, 3, 4, I think should be okay. If they're specifically mentioning to write more insights, that's a different thing. But I think otherwise it should be okay. 3, 4 insights should be okay. Okay. Looks like we have less people today, although today is going to be like the most important lecture on probability. I think pretty much all the doubts that were there until now should hopefully be covered today. Any questions, meanwhile, any questions from, let's say, the last probability lecture? Did you get a chance to look at the recording again for any doubts that you had? I think a lot of people were confused with conditional probability towards the end. But I am hopeful if they would have gone back and looked at the video, it should have been clear. Categorical handling takes time. Numerics easy to plot. Correct, Navru. I think we'll also have part of EDA lecture will be specially we have a topic called categorical variable encoding, right? So you'll understand, you'll learn different types of encoding methods. So all of this will come. No, Raku, you didn't miss anything. Who would evaluate case study? I think TAs should be evaluating, if I'm not wrong. I think for specific some business use cases, your peer might be also evaluating, but I don't think for these ones your peers would be evaluating. Quick recap. Yeah, I mean, today's lecture is gonna be like, a summary of what we covered. So don't worry. Just focus a lot. Today, I urge you to properly focus, and we'll do some quizzes as well. I have some quizzes which are tough. So I would say most of you would not be able to solve it within the time. So we'll probably just do a discussion and then I'll launch the quiz. But yeah, I mean, don't get disheartened, disappointed with yourself if you're not able to solve it right away, but just focus on the content. All right, so let's waste. I think it's 9:06, so we should just get started. As Muthu was mentioning, quick recap from the last class. I'll spend first 20 minutes in just recapping, but in a different way. All right. All right. So today, let me share my screen. And let me try to sort of build a mind map which can be helpful for you to revise probability. All right, whenever you want to go through it during the interviews or otherwise as well. All right, so first thing we started with talking about one event, right? How do you calculate probability if you have only one event of your interest? All right, so let me draw a sample space. All right, so this is a sample space. This is a Venn diagram, right? We did in the last class, and this is the event of our interest. All right, so let me color code them. So blue is the area of our interest, and maybe green is the other remaining area. All right, so the green is the remaining other area, and blue is of our interest. So how do we calculate P of A in this case? All right, remember, I think from the first class we did number of favorable outcomes, right, upon number of total outcomes, right? I can also mark this as probably the area, let's say in the blue. The area in the blue, all right, that will be part of numerator. And in the denominator, we'll have blue as well as what? Green, correct? And right. I don't think there should be any doubt in here, so we can just quickly move. All right. The whole idea is that you put favorable outcomes on the numerator and total possible outcomes in the denominator. All right. Even one event case, I think very simple. All right. Now let's come to the important part, which is when you have two events, right? So you are interested in knowing something about two events. So two events are of your interest. All right. So first, let me ask you a question. All right. How a different by how many different ways can you let's say represent these A and B events on a Venn diagram? All right, so I feel there are two possibilities and they are exhaustive probabilities. There is nothing like a third probability. So first one, either they don't overlap. Second one, they overlap. All right, do you know of any third possibility besides this? Is the screen not shared? Is the screen shared now? Okay. So I think we've not missed much. All right, we have a sample space. All right, and we had event A. All right, let me just do it again. We have a sample space and we are interested in knowing the probability of event A. All right, so there is only one event, correct? There is one event and I've marked this with what? Blue color. And then green is the part I am not interested in. All right. Is that okay? Are you guys able to follow up now, or should I like draw it again? Drawing it again probably just would take up a lot of time. All right. So event A, just one single event. It's there in the sample space. How do we calculate the probability of A? We take favorable outcomes in the numerator and total outcomes in the denominator, right? So what are the favorable outcomes? The one in the blue, right? What are the total outcomes? The blue plus the green area, correct? All right. So this is the numerator. This is denominator. Very simple. All right. Now I finally came to the second part, which involves two events. So now we have two events. We have A and we have B. All right. And what I was asking you is that how many possible ways you can represent these events A and B on a Venn diagram. All right. So first condition, they'll overlap. All right. Either A and B will overlap. Second condition, they won't overlap. All right. Do you know of any third? Can you think of any third possibility? Can you think of any other possibility besides representing A and B within this Venn diagram? All right. So it's simple. It's mutually exhaustive. Either they'll overlap or they won't overlap. Correct. Right. So when they overlap, we call them not mutually exclusive. All right. And when they overlap, we'll call them mutually exclusive or disjoint. Correct. Right. So every time, whenever I am provided with two events, the first question that I have to ask myself is whether it's mutually exclusive or not mutually exclusive. All right. So this is the summary. First question that you have to ask is whether it's mutually exclusive or not mutually exclusive, right? So one is entirely inside. I think this will also be the case of non-mutually exclusive, right? Right. So even if there's an overlap, that means they are not mutually exclusive. Correct? Correct, Sri Ramya? Correct, Rahul? Does it make sense? Does it make sense? Right. Let me just remove this. All right. So first question that you have to ask is whether events are mutually exclusive or not. All right. Next question. I might be interested in knowing different kinds of questions with these two events, right? A and B. All right. First kind of question, I might be interested in knowing union of A and B. All right. I might be interested in knowing intersection of A and B. I might be interested in knowing just the probability of A or probability of B. All right. This is slash. That means just one of them. All right. And then I might be interested in probability of A given B or vice versa. All right. These are the four possible kind of questions or the kind of probabilities you would want to know. Correct? Is that make sense? Does that make sense? Cool. Now, what are the different names for it? Let's just summarize that part as well, maybe. So this can be written as maybe A or B. All right. How else it can be written? It can be written as A plus B. How else? I can say either A or B. All right. All right. Any questions in here? Ankit, how was first and third different? First, I am saying, okay, let me just not write it. Let's say I am interested in knowing the marginal probability, just probability of one of the events. All right. So I can ask question as something like PA or maybe PB. All right. Cool. So what else? How can you write this thing? All right. You can write A and B. Right? A and B. All right. What else you can say? Maybe you can say joint probability of A and B, right? Remember in the last class we did joint probability, right? Which means probability of A and B occurring together, right? What else you can say? You can say P of both A and B. Does that make sense? All right. Let me just add P here, everywhere. All right. Does it make sense? Everyone, give me a thumbs up if it is clear, and we'll just go ahead. Perfect. Now this, if you remember in the last class, we discussed, it's called marginal probability. All right. And of course, when it's when it is talking about just one event, that's more or less like this only. But we'll see, what difference do we have when we have two events of our interest, but we are interested in knowing the probability of just one event. All right. And the last but not the least, I think we did this. This is called what? Conditional probability. All right. All right. Now, before actually starting this, let me just create some more space. So let me say, Perfect. So I think before starting this, we discussed that if A and B are given, I think the first question that you have to ask is whether they're mutually exclusive or not. So let's cover both these cases one by one. All right. So let me say case one here. Case one is when they are mutually exclusive. What does it mean? The Venn diagram would look something like this. All right. Don't worry, we'll do examples of each and every case. We'll do a lot of practice today. That's the whole agenda of this class. All right. But let me just summarize what we've discussed and probably just create like a map which we can use further. All right. Now think about it. This is your Venn diagram, and this is A and this is B. All right. And you are saying that I am interested in A union B, right? Which means if there is A, all right, that is my favorable outcome, right? If B occurs, that is also my favorable outcome. And if both of them occurs, that is also my favorable outcome, right? I am fine with occurrence of A independently. I am fine with occurrence of B. I am also fine with the occurrence of A and B, right? But we don't have anything A and B here. Do we have anything intersection? Do we have anything common between A and B? No. All right. So can I just add the probabilities of these two events and say that will be the total probability of occurrence of A and B, right? So I can just say this case, the total probability would be P, A, and B. All right. Was that clear? Is that clear? Does it make sense? Rohit, I'll come to your question when I'm like done with this diagram. I'll come to your question. Don't worry. Perfect. Let me just summarize this. All right. So let me think about case two. All right. What was my case two? Case two, not mutually exclusive. All right. What does it mean? Not mutually exclusive. Essentially, they overlap. All right. So these events are overlapping. All right. Mutually exclusive. All right. Now this time I have these thing overlapping. All right. So what I'm interested in, I am okay again with A. I am okay with B, and I'm okay with A and B. All right. So maybe let me just take the probability of A again. All right. A again. I took the probability of A. Let me also take the probability of B. All right. So I took the probability of B. What is it? All right. I took the probability of B. All right. Now, next, if you notice, we have taken this part. We have taken this intersecting part, the overlapping part, 2 times. All right. So we'll have to subtract it once, correct? So we took it as a part of this circle, and we also took it as a part of this circle, correct? So we took this part multiple times. All right. So I'm just going to subtract this part. And then in case of not mutually exclusive event, this will be your answer for A union B. All right. Any questions in here? Any questions for this specific part? Otherwise, general questions I'll come later. Any questions? Perfect. So I think somebody was asking about talking about the third possibility, which was this, right? One is inside this one, right? So in this case also, if I let's say maybe take the first circle, all right? So this is A. Then I maybe take the second circle, which is what? The inside one, all right? So B. All right. So this one I have taken multiple double times, right? The inside circle I've taken multiple times. So maybe I can just say subtract B, and this will be the answer finally A. All right. This is the union, right? Does it make sense? Cool. Perfect. All right. So before going to let's say intersection, let me just conclude this part with a couple of lines. First thing, as you notice, irrespective of whether it was mutually exclusive or not mutually exclusive, we are adding. All right. It's just that we are not subtracting an intersecting part. Why? Because there is nothing like an intersecting part, right? So this actually is the general formula. All right. This PA plus BB minus P intersection A intersection B would be the general formula for calculating the union. All right. And if in case there is nothing intersecting, this part will be 0, right? Since you are adding these probabilities to find union, usually we call this rule as addition rule. All right. So this rule that we have learned here is called addition rule. All right. Any questions in here? And I can just take up one or two doubts related to union. If you have any doubts related to union, please feel free to ask. Otherwise, we can go to the intersection and we can quickly finish this summary. Those who are feeling this is too easy, keep focusing. I'll come. This summary would include some interesting parts as well. So keep focusing. Don't lose any focus. Rohit's A intersection B and B will be mutually exclusive since they are not overlapping in the diagram. Yes, Rohit, correct. So you are saying you are subtracting, you took A and you subtracted the intersecting part of A and B from A, right? So which provides you kind of this kind of a thing, right? So these were the two circles, all right? So in first case, you got this, something like this. And in the second case, you got something like this, right? So these will be mutually exclusive, yes? Yes, why? They're disjoint, right? I hope it's clear, Rohit. They'll be disjoint. They'll be mutually exclusive. Perfect. All right. I mean, 3 events, 4 events, it scales up. Usually you talk about 2 events only, but all these formulas are scalable and maybe we can see towards the end of the class. All right. But nothing to worry about. All of it scales up. All right. Cool. So let's move to the cases of intersection. All right. I'm going to finish it and then I'm going to take all the questions. All right. So as we discussed here, we are interested in the cases where both A and B should occur. All right. So I am saying that A should also occur. A should occur and B should also occur. So they both should occur. All right. And which area would represent that both of them are occurring? This area, intersecting. The area which is intersection between both of them would actually represent both of them occurring together. All right. Now, case one, again, as I said, you should be first asking the same question every time you do this activity. Are the events mutually exclusive or not? Let's say case one where mutually exclusive events are present. All right. What would be the probability of P intersection A, P intersection, sorry, A intersection B, probability of A intersection B when events are mutually exclusive? What do you think logically? What do you think logically? What would be the probability here? 0, right? I think this is very easy to understand. There is nothing intersecting between these two events, so the probability would be 0. All right. So let's dive into the case 2, which is more interesting. Again, not mutually exclusive event. All right. How do I represent not mutually exclusive events? There should be some overlap between A and B. All right. This is the representation that we have for not mutually exclusive events. All right. So I'm going to go a little more detailed here. So try focusing over here. This is the most important part. Now, within this, actually, there can be 2 cases. All right. Clearly, if the events are mutually exclusive, that means they are disjoint. Intersection of them would be 5, right? So that's like a trivial case, right? So the interesting case would be when they are overlapping. There is some overlap. All right. And even if there is an overlap, there can be 2 possible cases. Either it's dependent or independent. All right. So either my events A and B can be dependent or independent, right? So let's try first understanding what let's try summarizing what independent and dependent events are first. All right. And then we can get to their formulas. All right. So case 1, let's say dependent. All right. So A and B are dependent here. All right. So what do we mean by dependent? All right. So assume that somehow I got to know that A has occurred. All right. What am I aware? A has already occurred. All right. And now that A has occurred, I am interested in knowing the probability of B. All right. Let me represent this probability with 1. All right. I'm just putting a 1 here just to differentiate. All right. There's nothing, anything about this 1. All right. This is just the probability of B. I'm just to identify it, I'm just adding a 1 in here. All right. As a subscript. Second case, let's say I know somehow that A has not occurred. All right. So for not, I'm actually putting a complement here. All right. So I'm saying now that I'm aware A has not occurred. All right. So here in this case also, when A has not occurred, I would be interested in knowing the probability of B. All right. I am interested in knowing the probability of B. I am saying, okay, now that I know A has not occurred, I want to know what is my updated belief. What do I believe about the chances of occurrence of B? All right. And that I'll represent with PB. Again, just to differentiate, I'll just put a small 2 here. All right. It's just PB. I'm just putting it to differentiate. All right. And in the last case, let's say I'm not aware whether A has occurred or not. Let's say I don't have any information. All right. So this will be a normal PB, right? This is the general probability of, let's say, event occurrence of event A, correct? If these events A and B are dependent, that means these probabilities won't be equal to each other. All right. Which means if A has occurred, the probability of B will be something else. If A has not occurred, the probability of B is something else. And then if I'm not aware, this is the general probability, which won't be equal to any of them. So any of them won't be equal to each other. All right. Is the idea of dependent events clear? First, the idea of the dependent events clear. All right. So knowing whether A has happened or not happened will affect the probability, will affect the chances of occurrence of B. All right. And that is why we are calling them as dependent events. All right. Now, how do we calculate the probabilities for this? How do we calculate? What am I interested in? I'm interested in calculating A intersection B, the probability of occurrence of both the events together. All right. Now, remember, whenever we used to talk about and, all right, so this is A and B, right? Whenever you used to talk about and, even if you've seen with Boolean logic, we used to use what? Multiply. All right. We have used addition here. We used to use what? Multiply here. All right. So I'm going to multiply two probabilities. All right. Remember, we used to, whenever we are taking, let's say, doing two events, let's say tossing a coin two times, we would multiply their probabilities, right? So first, knowing that A has happened, I'll say probability of A. All right. But now that I am aware that A has occurred, the probability of B will instead be written as probability of B given A. All right. This is nothing but this PB1, right? What is the probability of B given that A has occurred? All right. So for dependent events, I will take probability of one event and then conditional probability of the other event given that A has occurred. All right. Since it's symmetric, since this can be written as this as well, and they both are same, I can also write PB, knowing that B has occurred. I want to know the probability of A given B as well. All right. And I'm simply just multiplying these events. Why? Because this is and. All right. Is this clear? This is just the revision that we are doing. We'll do enough of practice today. Don't worry. But is it clear? Crystal clear? No, I think someone marked no. Please free to ask any question that you have. Bayes theorem, we'll come to Bayes theorem. This is not Bayes theorem. We'll come to Bayes theorem. We'll use these formulas to derive Bayes theorem. It's not Bayes theorem. I'll come to independent part, Muskan. I'll come to independent part once I'm done with dependent. All right. So just to summarize, dependent part here, dependent events means occurrence of one event would affect the occurrence of the other. All right. So if I'm aware that A has occurred, the probability of B will be something different, not equal to probability of original probability of B. And if A has not occurred, that probability will also be different than the original probability of B. All right. And here, to calculate the probability of A and B, we just basically multiply the probability of two events. So first I'll take the probability of one event. All right. And then in the second case, I will take a conditional probability of B, right? Because now that we are aware that A has occurred, instead of using PB, I will say PB given A, right? Because I'm already aware that A has occurred. All right. And similarly, instead of this, I can do PB. I can start with PB and maybe say PB of A given B. All right. So let's talk about independent event. Let's talk about second case within not mutually exclusive events, independent case. All right. And here, what we'll use the same formula. I'll say here also, P of A given B can be calculated. Let's say I can start with event A, and knowing that A has occurred, I would want to know what is the updated probability, what is my updated belief of A. All right. But remember that A and B are independent. All right. So do you think that probability of B given A would be actually equal to probability of B itself? Do you think, does it make sense? Does it make sense that probability of B given A would actually be probability of B itself, right? So we can just simply replace this with PB. All right. Why? Because irrespective of whether A has happened or not, I don't care. Why? Because A and B are independent. I don't care whether A has happened or A has not happened. I can just simply multiply the probability of B. All right. So this will be this will be the case of independent events. All right. So we'll understand. We'll do all the questions to understand these things again, but just deriving some formulas. All right. All right. So just the way we actually took a general case over here, let me just say that the generic formula for calculating the joint probability, remember it's the joint probability that we are calculating, would be what? PA multiplied by PB given A, or PB multiplied by PA given B. All right. And if it is independent, all these conditional probability will actually be equal to marginal probability itself. Why? Because these events are independent. All right. But this can serve as the generic formula for calculating the joint probability. Correct? Just like this formula can serve as the general formula for calculating the union. All right. So I am just creating this this table, although I know it's very messy to have these two things together. Trust me, all of this will help you a lot. I can just probably digitize it later and share it with you, and that can actually work as a cheat sheet for you later. All right. So that's why I'm just trying to summarize everything in one single go. All right. So let's any question before we move to marginal probability? Any question before we move to marginal probability? No, Sri Ramya, is dependent and independent case applicable for union? No, actually it doesn't matter, because we are interested in all kinds of events. I am fine whether A happens or B happens or both of them happens. I'm just interested in taking union of everything. All right. Union means take a superset of everything. All right. Take a union of everything. So I don't care. Even if, I mean, these events can actually be independent or dependent. I don't need to look into it. All right. I don't need to look into it. Does that make sense, Sri Ramya? Why? Because we are taking a union. Does that make sense? The probability of union won't differ, right? The probability of union won't differ, irrespective of whether they're independent or not. Okay. I'll just unmute you. I'll just unmute you. Yes, Sri Ramya. Very quickly. Otherwise, we can take up more questions towards the end.
Yeah, hi, I'm sorry to disturb, but you might.
No, that's okay. That's okay. Yeah.
You might want to take a fresh page. I'll just give you an example. Okay.
Okay.
Say, suppose. Okay. I'll take a coin to make it simple.
Okay.
A coin is tossed. Okay.
Sorry?
A coin is tossed.
Okay.
And if I say the probability of, event 1 is head occurs and event 2 is tail occurs, only two events are there. So I would say if the probability of head
Sorry. I actually missed it. Can you speak? I don't know if it's the network or something else, but can you speak a little slower? Like in terms of speed. Hello? Sri Ramya, are you there? I just lost you. Sri Ramya? Hello? Am I audible, guys? Am I audible? Right. I don't know what happened. Sri Ramya, it's okay. Don't worry. We'll probably just take this up later. I am super sure. This is all good. We can take it up later. It's okay. Don't worry. I'll sure we'll take it up later. Any more questions related to either union or intersection? Feel free to ask. We won't touch base this again. You can make. Do you want to come again, Shrima? Actually, let me just probably just cover this summary, and then maybe we can do it before solving the questions. Shrima? All right. Perfect. All right, so the next one is what? My marginal probability. All right, so I am here interested in events like maybe knowing a probability of B, or let's say probability of A. All right, it's the same thing. I mean, the whole idea would be same. We can just either be interested in calculating the probability of one event. All right, so let me try dividing this in cases again, once again. All right, and this might be a little tricky to think about it, but this, I mean, one of the cases. All right. So first, let me consider a mutually exclusive event again. All right. How will mutually exclusive events look? They will look like this. All right. Now this, let's say, is blue, which is A, and let's say the green one is B. All right. And let's say that I am, for this specific graph, interested in knowing the probability of B. All right. I'm interested in knowing the probability of B. All right. What would be my favorable outcome? What would be my favorable outcome? What would be the color of my favorable outcome? Blue. Correct. What would be my what would be the outcome of my what would be the total outcomes? What would be the total outcomes? Total possible, this is blue plus green. All right. So this will be simple, blue plus green. All right. But this use case is simple. All right. This case is simple. All right. Now let me take case of the not mutually exclusive event. Right. Not mutually exclusive event. How will they look? They will somewhat overlap. All right. They will somewhat overlap. Correct. All right, so here again, I am interested in knowing the probability of B. All right, so let's actually try to color code our favorable case. All right, so there are two favorable cases that I'm interested in here, this intersecting area. I hope the picture is not small. Give me a heads up if the font and everything is clear. All right, or I'll just try to zoom. All right, okay. All right. Okay, so I'm interested in the probability of B. All right, this event, this right circle is B. Right, the first part I've marked with red. Right, this is my favorable outcome. Right, what is the second area which I'm interested in? I'm interested in this area. Correct. So both this red and yellow makes my favorable outcome. All right. So maybe just because these are two possible events, let me actually name what these are. First case, B happens, but A doesn't happen. All right. Second case, sorry, this was not the first one. This was the second case. So first, let me try the red case. All right. So red case is what? Both B and A happens. All right. So A, B. Correct. Both A and B happens. Red represents what? Both A and B are happening. All right. What does yellow represent? Yellow represents that A doesn't happen, but B happens. All right. Is there any other way that I can get B? Is there any other way that event B can occur? All right. I am saying that event B is occurring. All right. Event B is occurring. So along with B, either A will occur or A won't occur. Correct. These are the two possibilities, right? I am saying that I am interested in knowing the probability of B. B can occur in two different ways. B either can occur through the yellow outcome or B will occur through the red outcome. All right. Maybe I can just add the probabilities, add these two possibilities. Why? They are mutually exclusive, right? Are they mutually exclusive? Do you understand that they are mutually exclusive? Do you understand this region red and this yellow region are disjoint? They are touching each other, but they are different. They're not overlapping, right? These regions are not overlapping, right? So I can just probably add P A B and P A intersection B, right? And that will be equal to my probability of B. All right, that will be equal to my probability of B, right? This, by the way, is also called law of total probability. Why? Because I am considering all possible ways in which B can occur. All right, I'm considering all possible ways B can occur. B can occur in two ways. B can occur either with B, sorry, A, or B can occur with not A. Right? I am just counting all possible cases of occurrence of B along with different events, and I'm just adding them. All right. So that's why this is also called law of total probability. I know this is this term that we have used is a new one. We've not learned it, but we'll take an example of this one as well. All right. Yes, PAB is P common B. Right. I mentioned it here. Okay, I forgot to mention it here. Maybe PAB or PA dot B. All right. Why they're mutually exclusive? What does it mean by mutually exclusive? Mutually exclusive means that they are disjoint, right? So they don't overlap with each other. Do you think the red region and the yellow region overlap with each other? Does the red region and yellow region, do they overlap with each other? No. They are mutually exclusive, right? If they are mutually exclusive, they can just be added together, right? Without subtracting anything, the way we had subtracted here. All right. I am just interested in knowing the probability of this big right ball. All right. Now, right ball is composed of two individual events. What are these two individual events? The red one and the yellow one. What is the red one? Red one says B occurs with A. Correct. What does the yellow one say? B occurs, but A doesn't occur. Correct. Muskan, is it clear now? Why they're mutually exclusive? They're mutually exclusive because they don't overlap with each other, right? So what all does it mean that I can just add them together without subtracting anything from here, right? Red is the part of not yellow part. Okay, so wait, let me just draw it here. So if this is the circle, this is a big circle, this is a big circle. I am saying that this is the red part, and I am saying that I am marking this as I am marking the other part this as the yellow part, right? Just this part. So maybe you can think that this is the red part like this, and the yellow part looks like this. All right. So they touch either, they don't overlap. Right? Does it make sense, Muskan, now? Okay, I didn't draw B, the ball B with yellow color. I just drew the other part, the remaining part with yellow color. Does it make sense now? Cool. All right. Very quickly, I'll go again for the case one, as somebody asked. I think it's the trivial one, though. I am saying that I have two events A and B, all right, and they are mutually exclusive. What does it mean by mutually exclusive? They are disjoint, all right. They don't overlap each other, right? Now, let's say this is the case of this example. A good example of this will be, let's say a die 1, 2, 3, 4, 5, 6. All right. Are they disjoint? Yes, they're disjoint. At one point of time, only one can occur, right? Only one can occur, two can occur, three can occur, four can occur, five can occur, or six can occur. Correct? So what is the favorable outcome if, let's say, I'm interested in knowing the probability of just two? All right. I can just say one case, which is the favorable outcome, and the total outcomes, right? Which is what? Six, right? All I'm saying here is that the probability in this case can be just as simple as this case, this one. Actually, this won't be green. This was not the right representation. It should have been with one more color. I would say, let me pick up. I mistake. I didn't consider this. I should have drawn one more color. Maybe let me yellow. Yellow is the part which is not green, neither green nor blue, right? So here it should be yellow as well. Does it make sense now? Does it make sense now? Mahuj? Correct. I just didn't realize that I should have added one more color. Does it make sense now? Correct. Cool. Perfect. All right, guys. It is still clear until now. Any questions, or otherwise we can move to the next one. You don't have to. So all I'm saying, Dilreet, is one thing. Okay, so I'll just conclude this part one more time. All right. I am saying that these are the two events, and I'm interested in knowing of this ball. All right. This B ball. All right. What is this B ball composed of? It is composed of maybe two things. Right. So this, and there is one section which is this, and then there is this other section which is this. All right. Now, I am interested in knowing the probability of B, correct? Now, B can occur only in this area, right? And this is composed of two possibilities, right? Either B occurs and A also occurs, which is what? The red region, all right? Or B occurs but A doesn't occur, which is what? The yellow region, right? And this would actually constitute the whole total probability of B, all right? Does it make sense now? Why I'm calling it total probability is just because this probability that we have calculated is using just combination of all possible constituents of B, event B. Right? I'm covering all possible constituents of B. Cool. Sorry. All right. So I believe no questions. Any more questions we have? We can spend one more minute. Otherwise, we can go talking about finally conditional probability. Actually, there is not much to really discuss in conditional probability here, but we'll conclude with the cases. Any questions? Yes, Sriramya, you can ask now. Can you raise your hand so that I can quickly?
Am I audible?
Yes, hi.
Hi. I was asking that in A union B case, right? I mean A or B case, you said dependent and independent events are same.
No, I am saying it doesn't matter. You don't need to know whether events are independent or dependent. You don't need to know this.
Yeah, but I felt there is a case wherein this probability could be different or where it matters. Like, for example, if you have drawn a card, right, from
Okay,
a deck of cards.
aren't we doing a coin?
No. I came back to card. I realized coin won't work. Okay, I came back to card. No, what I wanted to say is in case of independent events, you replace the card. But in case of dependent events, you don't replace the card. So that probability will differ, right?
Okay, so let's actually do one example. So the point is, Sriramya, you're trying to sort of cram. All right. So you've remembered that in the case of independent, what did you say? In the case of independent,
You
do what?
replace the card.
You replace the card. Okay.
Yeah, the first
And
experiment you
in
pick
the
up
case of
card,
dependent,
and in dependent events you
without replacement, right?
yes.
All right. So okay, this is fine. Or whatever you've said, this is okay. But can we go ahead and try calculating A union B? Can you give me an example where I have to calculate A union B?
Yeah. So let's consider P of A is a number.
Okay, so A is a number.
Yeah, and B is red card.
Okay.
Okay, or let me be very specific and say it is a diamond card so that we have the probability less.
This one, red, B1.
B1, we'll make it diamond.
Okay. Oops.
Yeah. So I just wanted to try two cases like with replacement and without replacement.
Yeah. So I'll be able to answer you. All right. All right. So actually, let's go. It's okay. I am just worried if this confuses people, but it's okay.
But
Okay.
if
So
you
what
want
can
to
you
clear that,
then?
it's okay.
No. Let's now that we've written this, let's just try. So you are interested in knowing the probability of A union B, right?
Yeah.
So I am saying either the card should be a number or diamond or both, right?
Yeah.
Right. So let me explain how would you let's just solve it. All right. So the first event A is a number. All right. Let me draw this with this. And how many numbered cards do we have? So we have 10 numbered
40.
cards in each suit. All right. Yeah. So there'll be total 40 numbered cards. Correct?
Yes.
Yes. Let's try making the diamond cards. All right. So diamond card certainly would overlap with this one. All right. How many diamond cards? So diamond is this, by the way, right?
13.
I'm just confused, right? Yeah. So there'll be 13 cards, right?
Yeah.
There'll be 13. This is 13. This is 40. And there'll be some overlap. What will be the overlap look like? This overlap will be
number and diamond is 10.
10, right? So I am saying you want to know A and B. All right. So the formula that I gave you was probability of A plus probability of B minus probability of A intersection B. All right. What is the probability of A? 40 by 52. Correct?
Yeah.
What is the probability of B? 13 by 52. Correct?
Yeah.
What is the probability of A intersection B? 10 by 52. Right? 40 minus 30 is 30, minus 13 is what? 17, if my calculation is right. So 17 by 52 is your answer, Sriramya, right? Sriramya, right?
Yes, 40 plus 13 is 53. 53 minus 10 is 43.
Whatever, 43, right? 43 by 52, right? The point here is, first thing, this is I don't know how and when you crammed it, saying ki independent is always replacement and without replacement is dependent. All right. I mean, independent dependent is a bigger concept, all right, and it just happens to be the case that in case of replacement, the events come out to be independent, and within in case of without replacement, the the events turn out to be dependent, right? So first thing, okay. Second thing, Sri Ramya, I mean, we'll explain this part as well. I am not saying that you're wrong, but it's just like the concept of independent and dependent is bigger than this.
Okay.
Second thing, like, this is the solution. I am still trying to figure out where do I need to know whether these events are independent or dependent. Where did I require that part?
Okay, so I mean, if I'm saying that there are two separate events and either a number or a diamond should occur, then I have to specify either a number should or diamond should occur in the first case or second case, or both the cases in either of the case. That also should be mentioned, and it becomes a totally different context. That's what you mean, is it?
Right. So actually, here we need to be clear first. What is the experiment? All right. The experiment that you have told me is that you have to take out one card out of 50, a card of 52, a deck of 52 cards, right? So you are taking out only one card, correct? And you are saying the probability of A union B as in either A can occur or B can occur or both can occur, right?
Yeah.
I'm saying, yeah. Did you get it?
I got it. And in case of replacements, it can't be one experiment. It has to be two experiments because I'll be having a new deck and then okay, I understood. Sorry for that.
That is why I think if you remember, I am not sure people were saying that, this instructor is trying to confuse. It's always a good idea to first write about experiment clearly, first part. Second, to be clear about the sample space.
In case of intersection also, then the experiment will be different, right?
Right. And we'll do those cases, and you'll be able to understand.
Okay, I'll not confuse further. This is enough. Thank you.
Right. So, I mean, just to conclude, guys, for the case of union, just because you're taking everything, you don't need to know whether these cases are independent or not. Well, technically, although we have illustrated mutually exclusive and not mutually exclusive events using Venn diagram like this or this, technically it's not possible to illustrate independent events or dependent events using Venn diagram. It's not possible. All right. There is another kind of diagram that we can use. Maybe you can check. They're Venn-like diagrams, and they're based on area, properties of area. So they are more of geometrical things. Although if time is left, I can later on talk about it. But it's just that it might be difficult. All right. So I will try not touching it because it's difficult. If time is left, we'll surely just cover it in brief. I won't take any guarantee that you'd be able to understand or not, but I'll try. All right, so let's do some questions. Let me actually just finish this summary and let's do questions after that, and you'd be clear. Or more questions actually I'll take up later. Sorry. Hello. Am I audible? Am I audible? And when did you guys miss me? Did you guys miss anything, or like okay, screen I'm sharing. Did you guys miss anything? I disconnected after the question. All right. So just to tell you, the question here is that I am interested in knowing the probability of A, and I am aware that B has already occurred. I am aware that B has occurred. All right. I am saying that the B has already occurred. What is the probability of A given B in case of mutually exclusive events? These events are disjoint. What is the probability of A given that B has occurred? Anyone? Any answers? More answers. I expect more answers. Think about it. Think about it logically. Okay. Try again. Dilreet, Ajay, try again. Okay, these events are disjoint. What does disjoint event means? That they cannot occur together. All right. What do we mean by disjoint events? They cannot occur together. Remember, the A intersection B was 0. That means they cannot occur together. And I am aware that B has occurred. What will be my updated belief of A? What will be my updated belief of A, knowing that B has occurred? Right. So the updated belief of A, knowing that B has occurred, would be 0. All right. So this is the tricky case, but I really wanted to cover it, and usually people don't cover it. But the good part about making this mind map or a flow chart is that we almost end up covering all corner cases. All right. So let's look at the other case that is also interesting. Case 2. All right. Case 2 is that they are not disjoint, or they are not mutually exclusive. All right. And I am interested in knowing again the probability of A, knowing that B has already occurred, given that B has already occurred. All right. Now that B has already occurred, what do I know? I know that my sample space has actually reduced to this area. Do you understand that this is my updated sample space? Because I know that B has already occurred. I know that whatever the event is happening is surely B. All right. I am interested in knowing whether A or B, what is the probability of A now that B has occurred, but I am telling you already that B has occurred. All right. That means the event is definitely B. Is that clear? That the sample space, I'm not saying probability, the sample space has reduced to B, right? Don't go with the formula. We'll come to the formula. We'll derive the formula. Don't go with the formula. Is it clear that the sample space is reduced to yellow part? What is the part which represents the favorable part? The favorable part can be represented by this area, this small area, right? I am saying I want to know the probability of A, given that B has already occurred. So what is my favorable case? My favorable case is the red one. All right. What is my total possible outcome? All possible outcomes. All possible outcome is this. Let me actually highlight this with blue so that you don't get confused. So this whole area. All right. So this whole area, which has like, both red and yellow. So, oops. Both red and oops. Don't go with the formula. We'll derive the formula in just a minute. But it has both yellow and the red area. Do you understand this? Does everyone understand what I'm trying to say? The favorable part is the red part, and the total possible outcomes, the total outcome is this, right? Because the sample space has reduced itself to B. All right. Now, how would you define this red area mathematically? This red area, if you look at this totally, is actually can be defined by P intersection B, correct? This area, can this red area be defined with P intersection B? P A intersection B? Can it be defined? How would you define this yellow and red area, this right ball? How would you define this red ball? P of B, right? And you have the formula that you have been remembering all through your life. But yeah, we have sort of done a small derivation by using Venn diagram as well, as in how to calculate conditional probability. Do you now understand what I've been trying to teach from last couple of class? that whenever you're interested in knowing the conditional probability, the whole sample space itself reduces. All right. And in the reduced sample space, I would consider my favorable outcomes, and I would consider that reduced sample space as the total possible outcome. And here you go, you have your formula. All right. Ajay, happy? We've been able to derive the formula. Right. This would have been a bit hard to imagine without writing, and that's why I thought maybe this approach would help. Arijit, for mutually exclusive event, should write as A is not related to B. Can you define related, Arijit? What do you mean by related? Because I know two terms. I know mutually exclusive, which means disjoint, and I know independent or dependent. What are you talking about? What do you mean by related? Okay, so you mean disjoint, right? You mean disjoint, right? Cool. So Arijit, think about it. The experiment is actually just one. We are doing one single experiment, whereas we are interested in two possible events, right? Just to give an example, let's say there is a deck of 52 cards, Arijit. All right. Actually, let me call you on stage. Arijit, can you raise your hands very quickly, if possible? Would you like to come on stage? Yeah. All right. So Arijit, let me try helping you through. Imagine. Hello. Can you hear me?
Yeah. Hi.
All right.
Hi, Anand. Yeah.
Let me actually give you an example to think about it. All right. So the experiment is that you want to draw a card from a deck of 52 cards, playing cards. Correct? This is your experiment, right? I am saying I am interested in knowing I will win. Okay, sorry, that was intersection. Sorry. This you've asked me about conditional probability, right? First thing, actually, let's talk about the events. Let's take an event A as probably taking out number 8. All right.
Okay.
And let's take event B as taking out Jack. All right. And okay. I am actually drawing one card. All right. So now that I've told you that the card that I have taken out is, let's say, a Jack. All right. It can be any Jack. It can be any of the 4 possible Jacks, but I'm just telling you that it's Jack. All right. What is the probability of A given B? 0.
But probability of A given B, meaning like, so given that B has occurred, what is the probability of B? So because they have no relationship together.
Given that B has occurred, you are interested in knowing the probability of A. You're interested in knowing the updated beliefs of A.
Right. The only thing that could happen is if it's a without replacement, then in that case it could be like 8. So there are 4 8s. So 4 divided by 51. And in case where we do not have, we have a replacement, then it should be 4 by 52, right? Because
Arijit, you're talking about experiments where you're doing something 2 times. Here I'm talking about just maybe drawing like maybe one card. We'll come to all of this theory with examples in your case. Here I'm just talking about the case where I'm just doing something and I'm interested in knowing. For example, let's say I'm drawing a card. I might be interested in knowing what is the probability that card itself is a red card and a king, right? So I'm talking about these kind of events, right?
Okay. So basically, in one draw, you're trying to determine what would be the value of probability of A given B has occurred. So it's one, even though there are 2 events, but you're doing it only once.
Right. So you are actually confusing between events and experiment. Experiment here is one, which is drawing a card. The events that I am interested in are 2. All right. And these 2 events can occur together as well. A red king can come in one single go, right?
Right.
Yes. But whereas drawing a red card and getting a king are 2 different events that I am interested in, right? I am interested in knowing the probability of how they can occur together.
Okay, I got it. That clears a lot the confusion. Thank you.
So I'll come to the kind of questions that you're talking about, but all of these formulas will be applicable there, and I'll explain how.
Sure.
All right.
Thank
I
you.
just wanted to
Yeah.
sort of summarize these things before we can do some questions, some practice. All right. I hope, Tulros, you are not asking any question. You are probably just explaining one of your colleagues. All right. If you have any questions, Tulros, Navroop, Rahul, as I can see the names, and Sri Ramya, I'll discuss later. All right. Perfect. All right. No, conditional probability is applicable both for independent events. We'll see. We'll discuss that. We'll discuss that with examples. But here, I just wanted to conclude that this is like, the formula that you have gotten. All right. So conditional probability of independent and dependent events is sort of covered here only. If I have to tell you, Sri Ramya, we have sort of covered it here also. I am just telling you how to calculate these parts now. We have sort of covered these things here somewhat, independent and dependent events. Okay. All right. So let's do some questions, and these will be very quick questions. So these are not quizzes. I have some difficult quizzes scheduled for you as well. But before that, let's do some practice just to, clear your concepts. All right. So let me actually first take up some examples of union. All right. Union is this, where I'm interested in knowing A or B, something like this. All right. So tell me, okay, so the experiment here is again drawing one card from a deck of 52 cards. Correct. This will be the experiment all through, and I'm just asking you a certain couple of questions. All right. So what is the probability of getting ace or a king? All right. So first thing, what we are trying to get is an OR, right? So we'll have to use plus, right? We have to use an addition rule, correct? Now next thing that we have to check is whether it's mutually exclusive or not mutually exclusive. Is getting an ace and getting a king mutually exclusive or not mutually exclusive? Mutually exclusive or not mutually exclusive? Answer. I'm not asking for final answer. Mutually exclusive or not mutually exclusive? Mutually exclusive, right? Why? Because ace and a king cannot occur together, right? If I'm drawing one card, ace and king cannot occur together. All right. So if this is an addition rule and mutually exclusive, what can be the formula? I can simply do P of ace plus P of king, right? What is the probability of P of ace? What is the probability of P of ace? 4 by 52. There are 4 possible aces in the deck, right? What is the probability of king? There are 4 such cards, all right? And this will be the final probability. I'm not going to do sum or anything, but yeah, this is my first example. Let's take another example. Now I'm interested in knowing the probability of getting a heart or getting a spade. All right. So first, let's try to understand whether it's union or intersection. It's union. All right. So we'll have to use an addition formula. We have to use an addition rule. Mutually exclusive or not mutually exclusive? Very quickly. Mutually exclusive or not mutually exclusive? Mutually exclusive. Why? Heart and a spade. All right. Can I get both of them together? No, I cannot get both of them together. All right. So they are disjoint, right? So they are mutually exclusive. So what I can do probability of heart plus probability of spade. All right. What is the probability of getting a heart? 13 such cards are present in the deck. What is the probability of getting a spade? 13 such cards are possible in the deck, right? And this will be my final probability. All right. Clear with the examples wherein we have mutually exclusive events and we have addition rule to apply. Third example. What is the probability of getting a queen or a black card? All right. So first thing, again, addition rule. We want to know union. All right. Mutually exclusive or not mutually exclusive? Are they exclusive or not? Can they occur together or not? They cannot occur together. Sorry, they can occur together, right? Not mutually exclusive, right? A queen can be black, right? So not mutually exclusive, correct? So in this case, I'll have to do P of queen plus what? P of black minus P of a queen and black, right? What is the probability of getting a queen? 4 by 52, correct? What is the probability of getting a black card? 13 by 50, sorry, 26 by 52, correct? Is that clear? What is the probability of getting both a queen or a black card, right? There are two different queens which are of color black, correct? A spade queen, or what is the other one? Club queen, right? So there are two such queens which are also black. Or is it 2 by 52? So this will be the final probability. I'll do one more question related to union, and then I can just ask for more doubts if in case if you have. These are simple, very simple questions just for like practicing what we've learned, and they will further scale up to more important, like more difficult things. So what is the probability of getting a king or a heart? All right. So I'm interested now in the probability of getting a king or a heart. All right. Again, addition rule. Again, not mutually exclusive, right? Can a king or a heart occur together? Yes, there are such king cards which are heart as well. All right. So I'll say probability of king. What is the probability of getting a king? 4 by 52. What is the probability of getting a heart? 13 by 52. What is the probability of getting a heart of a king? Sorry, a king of a heart, right? 1 by 52. Is that clear? Give me a heads up if all of these 4 examples were clear and also helped you getting your concepts clear about union. Remember, we want to know is that all we want to check is whether we have to apply addition rule and whether the events are mutually exclusive or not. And basis that we can take a decision and we can go ahead. We'll come to dependent, independent, Mohammed. For the case of union, we don't need to consider whether it's union or not. Sorry. Independent or dependent. All right. So let's take examples of intersection where we'll see dependent and independent as well. All right. So Sri Ramya, I would specially request you to focus on it. Here we are trying to go from first principles. So forget everything that you remember that, this should be without replacement, this should be with replacement, and whatever we should do, we'll try to do everything from first principles. All right. I should not have written independent. I should have written intersection. And naturally, you will understand that all these rules that you've learned follow. All right. So here, I am interested in taking out 2 coins. All right. All right. So I have 2 coins and I toss them. All right. And I am interested in knowing what is the probability of occurrence of head on the first coin and tail on the second coin. All right. First thing, it says and. All right. So I have to use what? Multiplication rule. Correct. Now tell me whether these 2 coins will be dependent or independent. Whatever comes on any of these coins, will it be dependent or independent? Sri Ramya, especially independent. Correct. So they won't be dependent on each other, right? So can I just write it as probability of getting a heads and probability of getting a tails, right? I can just simply multiply them, right? Because they are independent, correct? Is everyone clear with this? Give me a thumbs up if everyone is clear with this. I can just simply multiply their probabilities, correct? So I can do 1 by 2 into 1 by 2, right? All right. Second question. All right. So this time I have 2 decks of card. All right. I have 2 decks. Remember, I have 2 decks. I just don't have 1 deck. All right. So, and what am I doing? I am drawing 1 card from first deck. I am drawing second card from second deck. All right. Let me just remove this. But understood the example, the experiment, I have 2 decks and I'm taking out one card in each of the case. All right. So here I am interested in knowing what is the probability that ace comes in the first card from the first deck and king comes from the second deck. All right. First thing, are we interested? Should we use multiplication rule or addition rule? Multiplication or addition? Multiplication. Independent or dependent? Independent or dependent? Independent. Why? These 2 decks are independent of each other, correct? These are independent, right? Can I just multiply their probability? So I can say P of ace multiplied by P of king. What is the probability of getting P of ace? What is the probability of getting an ace? What is the probability of getting an ace? 4 by 52, right? What is the probability of getting a king? Again, 4 by 52. And I can just multiply it. The question, Mohammed, is that I have 2 decks all right? And from each of these decks, I'm just taking one card and one card, all right? I'm just taking one card from the first deck, I'm taking one card from the second deck, all right? What is the probability that I get ace from the first deck, and what is the probability that I get a king from the second deck, all right? Again, it's a joint probability. We will do multiplication, and these events will be independent, right? You can imagine intuitively that there'll be independent events, right? Is that clear, Mohammad Rashid, now? All right. So something to focus on here. I did what? I had two decks here, right? I had two decks, and I took first card from here and I took second card from here, correct? Can you actually think of this experiment as probably taking out one card from this deck? All right, so I took one card from this deck, and I am interested in knowing what is, if it's ace or not. And then what I did is I actually replaced, I just put back that card again. All right, I'm putting back that card again after seeing what it had, right? And then maybe I can just take out a card again from the same deck. All right, can you imagine, are you able to imagine that these two experiments that I've done are same? Can you imagine, are you able to imagine that they are same, right? So this is actually called with replacement. All right, why with replacement? I replaced it back. All right, and why this is independent? Because after replacing, the sample space remained same. Earlier, what was the sample space? 52. Now what is the sample space in the second time? 52 again, correct? Did the sample space change? No. If sample space didn't change, then if I take a card again, would that probability of taking out second card be dependent on the first one? What happened in the first case? No, correct? And that's why this is the case of independent events. All right. Now, I hope, Sri Ramya, you don't have to remember independent is the case with the replacement or without replacement. Now you can clearly see that with replacement means that you are keeping the sample space same, and that's why it's independent. What is the probability of getting an ace or king from either of the decks? Does it become an example of union or independent events? This is actually the same case over here. This is not in the scope of the class. It's not used in data science. But just to answer your question, Sri Ramya, you'll have to multiply 2 with this same probability. Why? Because you're saying I am fine with ace and king, and I am also fine with king and ace. All right. So it's this probability multiplied by 2, because you are fine with both kind of patterns. All right. You will just multiply with 2. So this is the case of combinatorics, not in the scope of the lecture. All right, so let's talk about the third case. All right, this time you have only one deck. All right, you have only one deck, and this time you want to take out 2 cards from the same deck. All right, what is the probability of getting a ace as the first card and getting king as the second card? How will we solve this problem? How will we solve this problem? First, what is the probability of getting ace? All right, first thing, actually, let's go by first principles. What did we discuss? What we need to ask is, first we need to ask whether it's the multiplication rule or the addition rule. Again, clearly you can see it's a multiplication rule. I don't need to explain it. All right. Now, whether it's independent or dependent, it will be dependent. Why? Because I am taking first card out, right? So I took first card out. All right. What was the sample space when I took the first card out? It was 52. All right. Now that I've taken first card and I'm not replacing it. All right. What is the sample space in case of drawing the second card? The sample space here would be 51. Correct? Because I am not putting back that card again. Right. So what comes in this draw is actually dependent on what card came up in the first draw. Correct? Will this be independent or dependent? Dependent, right? Clearly, you can see that it's the case of dependent. Why? Because what is this card will also change the probabilities of what comes in the second case. Correct? Give me a thumbs up if this thing is clear to everyone, and we can finally go to the solution. Clear? All right. So first case, what is the probability of getting an ace? There are 4 such aces possible in the deck, right? Now I multiply. All right. Actually, let me just write formula wise first. and then I can put the numbers maybe. So I'll say I want to know what is the probability of ace, and now I want to know probability of king given ace. Why would I say given ace? Because drawing an ace and king in this case are not independent, or they're dependent on each other, right? So I'll use a conditional probability, right? Why? Because I'm already aware that ace has come out in the first case, right? Ace has come out in the first case. So I now want to know what is the probability of king given that ace has come in the first draw. All right. So what is the probability of ace? 4 by 52. All right. How would you calculate the probability of king now that you know that ace has come out? All right. Now that ace has come out, what is the reduced sample space? Remember, in this case, the sample space reduced to B. All right. What is the reduced sample space here? 51. But what are our favorable number of outcomes in this case? Remember that ace has come out, right? So all the 4 kings are still present in the deck, right? So still the favorable number of outcomes are 4, correct? Does that make sense? Do you now understand this is probability of king given ace? But it may or not. Mohammad Rashid, can you just would you mind coming on stage, and if you can just ask? I'm not very sure what do you want to ask really. Feel free to ask me maybe after the class or now, but let me know if you're able to understand or not. Yes, Rashid. Am I pronouncing your name right first of all? Hello. Hello. Rashid, can you hear us? Hello. Can you hear me? Mohammed, hello. I'm not able to hear you. Rashid, you're not audible. Can you try can you try writing down? Or maybe we can just take it up towards the end of the class. No worries. No, probability of king given ace is actually not equal to probability of getting king. All right. Now, knowing that ace has come out has actually changed the whole sample space, right? So instead of doing probability of king, you will use probability of king given ace here, right? Because getting king and ace are not independent events. They are dependent on each other. Remember, what did we discuss for independent events? We discussed independent events. To calculate the probability of A and B, you'll use P of A multiplied by P of B given A, right? Muthu, is that clear? Right? And this is the generic formula. I've said that this is the generic formula. You would replace P of B given A by P of B only when the events are independent. Otherwise, this is the generic formula that you have to use. So always remember, this is not the generic formula. You always have to, if you are given P of A given B by, in general, the formula will always be this. This is the base formula, all right? And only if in case events are independent, you will replace this and it will be simply PA multiplied by PB. I think Ankit, is Ankit here in the class today? Ankit, are you here? Yes, I am assuming that ace is drawn here because we are talking about the favorable. All right, Ankit, do you remember that I think when I was teaching, you were confusing and you were saying that I can replace P of A by B is equal to, I can make it P of A into P of B, right? And I said that it's not possible, all right? You cannot assume that events are independent and you cannot directly use this formula. Do you remember this conversation in probably our first probability lecture? I don't know if you remember or not. Yes, in the first class, Ankit. I think you also came on the call maybe. Because it was like, this was PB down there and you said, this can be cut and the final answer will be PA. First or second class, I don't remember. Okay, right. So I'm just telling you, nothing went south. It was all clear. Probably it's just that now I'm summarizing everything. It makes things clearer, I believe. All right. Perfect. Guys, give me a thumbs up if it is all clear. Then probably we'll just do one one or two simple exercise, and then we'll take a quick break. All right. So get ready for quiz one. I'm gonna launch my quiz one. All right. So quiz one. First quiz wouldn't require you to. Where are the quizzes? Okay, this is poll. Sorry. First quiz wouldn't require you to like probably have pen or paper, but otherwise I would suggest that for quizzes you may require to like do some calculations. So keep your calculator and pen and paper handy. All right. So first quiz only for 20 seconds. What is the probability of two disjoint events occurring together? What is the probability that two disjoint events are occurring together? Perfect. I think most of you have answered it right. Ankit, I'll come to your question. Very quickly after this. So I am saying that there are two disjoint events. All right. I am saying what is the probability of these two events occurring together? All right. So what is the probability of these two events occur together? No. If one happens, the other cannot happen. If this happens, this cannot happen. All right. So the probability of occurrence of two disjoint events would be equal to 0. All right. Give me a thumbs up if it is clear to you now, if you are mistaken earlier. All right. Perfect. I couldn't check who answered it fast, but I'm not sure if it matters a lot. I think most of you could answer. Ankit, can you raise your hand very quickly? I can just probably understand your doubt and very quickly explain. This doubt might be common for other people as well. Yes, Ankit. Hi.
Hi, Anant. Yes. Yeah, so just wanted to understand, I mean, while you were explaining this part of here.
Where? Can you point it?
Yeah. In the intersection part. Yeah.
Okay.
You could just come down. Yes. Up there. This formula itself on the one deck, the third part.
The third.
P ace comma king. So when we say ace comma king, what exactly are we meaning here? Like
This is the joint probability. When I say P ace comma king, this is actually means P ace intersection king. I am interested in knowing what is the probability that both of these events are occurring together.
Okay, so it's only the probability of both of these events occurring together. And however, for the other scenario, go ahead.
Yeah, joint probability. So if I can show you, I think I've mentioned it here as well. P A comma B and joint probability.
All right.
Yeah.
Okay, so it is both of these events occurring together. All right.
Right. Do you have any questions related to you were saying I am also confused between P of A given B.
I was thinking, I mean, every time I saw ace comma king, I was thinking of it as A given king, ace given king. These two are connected.
So this actually is probability of B A only. All right, and I'm interested in knowing the probability of A only, but I'm saying that the other information that I have is that knowing that B has occurred. All right, so I am already told that B is occurring, and that is why my sample space total would actually reduce to the sample space of B. Remember this case where my new sample space became this thing, right? Which is what B, right? And here now I'm interested in knowing what probability of A only, right? This is P A given B, right? Right. If you still have any questions, actually, I mean, for a few people, I'm just telling, probably just going through this lecture recording once more would be really helpful. But this is actually this whole summary is a gem. So if you can just understand this once, you can just very quickly every time go through this and you would remember all the things in one single go.
All right. Yeah.
All right. Thanks, Ankit.
Thanks.
Yeah. All right, guys, anything else? Or are we good? I'm going to do one more question before we take a 5 minutes break. at 10:30 or 10:35. Perfect. So second question, probably for second question, I'll have to give, I mean, it's a little difficult. So I'll have to probably just help you understand the question first. We were to do it in the last class also, we couldn't. So there is a manufacturer, all right. There is a chip manufacturer, all right. And this chip manufacturer somehow knows that 2% of the chips are defective, all right. This manufacturer by default knows that 2% of the chips are defective, all right. Now what else? Let's say suppose an inspector comes to the factory, all right, and he randomly, out of all possible I mean, there might be like a sack of chips, I don't know what, or there'll be a lot of chips. He randomly picks out 4 chips, all right. So 1, 2, 3, 4. He randomly picks 4 chips. First, tell me, will picking these 4 chips randomly independent or chips like processor chips. Otherwise, I would have said chips packets probably. Can someone tell me, will randomly picking these 4 chips independent of each other or dependent? Independent, correct? Intuitively, you can understand that these will be picking up these will be an independent process. So just a hint to solve your question, you'll have to probably multiply these probabilities of getting 4 of these chips. All right, this is a hint for you. All right, so these are independent events. You can just simply multiply these. All right. Second thing, now I am interested in knowing what is the probability that at least one of them chips is defective. All right, I am interested in knowing what is the probability that at least one of them will be defective. That means what is the probability that I will be charged? What is the probability that I'll be charged? All right, this is the probability. Okay, so let me also give you something more before I launch the quiz. All right, I have already told the question, so you can start solving. If you want, don't answer it in the chat. I'll launch a quiz. All right, so the probability of defective chip would be 0.02. Probability of not defective would be what? 0.98. And this thing, probability of at least one of them being defective, can also be written as 1 minus probability that none of them will be defective. All right, think about it. I can just subtract it from 1, and this probability is actually equals to probability of 1 minus none of them will be defective. All right, so I think I cannot give more hints, and I'm gonna launch this quiz and looking for an answer before we go ahead. No, it doesn't depend on total number of chips, Sri Ramya. We'll look into it. I have given you percentage. When you are given percentage, you are sort of like, you can consider 100 chips, right? And you can just work with percentages. Guys, please participate. I see 53 of the students joining here and only 9 users have answered the question yet. You're still left with a couple of more seconds. Think about it. There are a lot of information here. There's a lot of information here. All right, so very mixed responses, and that's okay. That's reasonable. I expected this. All right, so let me actually decode a couple of things. By the way, oops, I was to tell names who have answered it correctly and very quickly. Okay, so I have Gautam in the first place. Then we have Rohit Sinha in the second place. Rajesh in the third place. Then we have Rahul Shivani, Pawan Kumar, Shriram, Dilreet, Karthik, Anirudh, and Tulrose. All of them answering it correctly and probably very quickly. All right. Okay, so for others, let's just try understanding. It's a difficult question, so don't worry. And by the way, you won't be like asked such questions in data science. We just somehow reached to a stage where I can explain Bayes theorem. So that's why I'm just doing all of this, all right? Don't worry, you won't ever be asked as a data scientist to solve these kind of questions. All right. So here I have two information. First thing, I know that the probability of a chip being defective is what? 0.02. All right. The probability of it not being defective would be 0.92, correct? Give me a thumbs up if this is clear. Oops, 0.98, sorry. 0.9. All right. Perfect. Now, I am interested in knowing that at least one of them is defective, which means I am okay with, okay, so these are 4 places. I can say I am okay with if one comes out to be defective. I am also okay with 2 of them comes out to be defective. I am okay with 3 of them comes out to be defective, or I am also okay with all 4 of them comes out to be defective. All right. What is the other remaining case left? 0 of them are defective, right? All right. So if I'm interested in knowing these cases, can I say that 1 minus probability of this one, which is 0 defective cases, would actually leave me to the probability of these cases? Do you understand this part? That if I want to know the probability of this part, which is either one of them is defective, 2 is defective, 3 is defective, or 4 is defective, instead of calculating this, I can just do 1 minus probability of 0 being defective. All right. All right. So I can calculate 1 minus probability of 0, which means none is defective. All right. And how would I calculate the probability that none of these 4 chips are defective? All right. So second hint for you, what was the second hint? Second hint was that they are drawing these things are independent. All right. So what is the probability of picking up a non-defective chip in the first case, in the first trial? All right. Sorry. What is the probability that I actually grabbed the first non-defective chip? 0.98. All right. What is the probability that I got again a non-defective chip? Again 0.98. 0.98 again, and 0.9 again, 98 again. All right. Now remember, these are 4 events. I think somebody was asking me early in the class, can we scale these things, these ideas to multiple events, more than 2 events? Yes, here are 4 events. All right. And here you would just multiply their probability of 4 independents. Why? Because these 4 events are independent, right? What you're taking in the first go doesn't matter, like doesn't change anything. All right. They are independent. You're just taking out 4 things together independently, right? They're independent. Correct? No. I am not taking it one by one. I am taking out together. Yeah, I mean, if I'm taking it one by one, then it will be independent, and then I can change the probability. Here I'm just taking out together, and that's why I give you a hint that he takes out these 4 things together, and that's why it's a random process. I mean, it can be dependent if you pick, let's say, 1 first, and then second, and then third, or 1 by 1. Also, the other way can be thinking about it, which a lot of researchers or scientists use, or your high school teachers might have also used. They say the stack or the lot of chips is so big, it's so big that taking out one doesn't change the distribution of this stack, doesn't change what is the probability of occurrence of a defective chip or a non-defective chip in this stack. All right. So the chips are in millions, it's in millions, that taking out one chip wouldn't change a lot of probability about defective chip and non-defective chip by taking out one. Yeah. Okay, Sriram. Got it. Yeah, understood now. Understood. Yeah, I mean, I thought, maybe I've just done the task by saying that, these are independent here, and then I'm taking out them together. All right. But I hope now it's clear. All right, perfect. Guys, okay, let me just actually keep this just so that, when you are, let's say, revising, you understand. There are millions of them. So taking out one won't affect the distribution of these chips in the stack. All right. I mean, this is an assumption, a theoretical assumption. The probability would actually become maybe 0.8, something, 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 very small minor change, but that we can just neglect. All right. That won't hamper the answer a lot. Give me a thumbs up if all of you are able to understand this. Give me a thumbs up, very quick, guys, very quick. All right. Then I think all of us, including me, I think we deserve a quick break. And I think we are left with only two things. I'll just quickly revise one of the examples of conditional probability, and we'll discuss one example of total probability quickly. And with these two things, we'll be quickly able to conclude Bayes' theorem as well. And after that, I mean, it will be an optional thing. If any one of you wants to stay, I can maybe try explaining an illustration of how to visualize independent events and dependent events, but that will be optional. And I won't also take guarantee that I'll be able to do a good job with that, because I have not prepared for that part. All right. Okay. Sure. All right, guys, 10:40. I'll see you at 10:45. I'll see you at 10:45. Yes, Saurav, we'll learn Bayes' theorem today. No, Sriram, we've not covered Bayes' theorem. Not in this class, neither in other earlier classes as well. We've not covered Bayes' theorem. Hey everyone, hi. Are we back? Are we back? I am hopeful that in a couple of days I can increase my speed to an extent. I don't know how. Like, is my speed less? Do I speak less slow, or do I cover the content slow? It's slightly less. All right. So I'll try to be a little faster. I don't know if it is because I take up a lot of questions in between or something. I somehow someday want to give you 10 minutes break. Many doubts as well, I guess. Yeah. I'll try to be faster. I am just like, worried if other people start missing on things. How many months is the course until November or October? The whole runtime of DSML part, which started in January, is 8.2 months currently. We've added a couple of extra lectures. Saurabh. Yeah. No, I think it happened recently because there was a lot of confusion. Otherwise, I am also not happy with like doing a lot of recap. For the last session, yes, it was like 2. Yeah. No, until I think October it should be good. Yes, I've been asking the team to sort of think about conducting a survey, but I'll check with the team. I mean, there are a lot of things I was actually trying to do, but I started taking up a batch, so I'm not getting a lot of time to do all of these things. Yes, until October, just for DSML. Somewhat lesser. I think probably until September. Then advance, yes. We'll make sure we're also training, specialized teachers for each and every module. We'll make sure that it's nice. Don't worry. Either at 9 months or 10 months. All right, so let's get back to conditional probability. And just we've already covered examples of union. We've already covered examples of intersection, and there's no point probably covering examples of this or this, although we can cover it maybe if time allots in the later. And then let's come to case of conditional probability. All right, A given B. All right. So here, let me define the experiment just so that you don't get confused. The experiment here is picking one card. All right, you're picking one card from the deck. All right, this is the experiment. What would be the sample space? The sample space would be 52 cards, correct? All right, let's define the events. Our first event is that the card is a diamond card. All right, our second event is the same card that is drawn is a red card, red colored card. All right, it's a red colored card. All right, here I am interested in knowing, what am I interested? I am interested in knowing probability of diamond given that it's a red colored card. All right, I somehow someone tells me that it's a red card. Now I want to know what is the probability of getting a diamond card. All right, so P A given B. All right, that is what I'm interested in. All right, so first let me draw the sample space to help you understand what is happening here very quickly. So this is my sample space. All right, and there'll be some, let's say, red cards. There'll be some black cards. All right, how many red cards will be there? How many black cards will be there first? 26. How many red cards will be there? There'll be 26 red cards, correct? I don't think there'll be any doubt. All right, so I'm marking this thing with red as B as well. Remember, the event B is getting a red colored card. All right, so this blob actually represents the event B, correct? Now let's draw the event A. All right, let me mark this event A with green color because I don't have any other option. So I'm marking this event A with green color. All right, so where would the event A lie? First tell me, where would the event lie? I'm not answering for the question. where would the event A, where would the circle event or event A lie within the sample space? Inside the red circle, correct? Because diamond is also a red colored, all the diamonds are red colored card, right? So this is an event A, all right? And how many numbers would be there here? There'll be 13 numbers, right? There'll be 13 numbers, all right? Now, what is the probability of first diamond? All right, first case, this is the sample space. Don't think about it right now. I just want to know what is the probability of getting a diamond. All right, so what is the favorable outcome? 13, right? So oops, sorry. What is the favorable outcome? 13 cards. 13 cards are favorable, correct? The green one, right? What is the total sample space? What is the sample space? Total number of outcomes? 52. All right, so the probability of getting a diamond without knowing anything is what? 13 by 2. I can reduce 13 by 2 to what? 1 by 4. So I'm saying there is 1 by 4 chance to get a diamond card if I'm not aware of anything. All right. Now, second case, I know that B has occurred. What is B? That it's a red card. All right. Now, what does this do? I said condition actually reduces the sample space. All right. So let me reduce the sample space. Let me say the new sample space is this one. All right. All right. The new sample space is this one. All right. So what is now the probability of diamond, knowing that the red card has occurred? All right. The card which has come up is a red card. All right. So I have reduced the sample space. All right. So what is the favorable count here? Now, what is the favorable count here? What is the favorable count? 13. Correct. What is the favorable count? Still 13, right? What is the total what is the total count count of all the outcomes? All the outcomes in the reduced sample space. All the outcomes in the reduced sample space, 26. All right. So this has become what? 1 by 2. Do you notice that the probability of occurrence of diamond has come from 0.4 1 by 4 to 1 by 2, 0.25 to 0.5. All right, the probability has increased, right? The probability has increased. And can you intuitively feel that if I don't tell you anything, and if I ask you what are your chances of getting a diamond, right? A diamond is equally likely as any other suit, right? So you'll say it's 1/4, right? There is 1/4 chances of getting a diamond. Now, if I tell you that the card that I've picked is a red card, all right, what is the probability that it's a diamond card? All right, red card can be of two types. Either it can be a diamond, right? Otherwise, what it can be a heart. All right. So do you realize that your probability that you'll get that it's a diamond card actually increases to half now? Because I've already told you that it's a red card. Do you understand this part? Give me a thumbs up if you understand this part intuitively. And you are able to understand what is conditional probability means now. So let's try to get this thing with your formula approach. So what is the formula of conditional probability? A and B divided by PB. All right. What is represented by this A and B? The green area, right? This green area, right? What is represented with PB? This red area. All right. So let me just say the red. The red area. All right. And maybe I can just write their probability as well. What is the probability of getting green part, right? How would you calculate the green part? It is actually P of A and B, right? Can you see that the green part is the intersection of the red part and the green part? Can you see that it's the intersection of A and B, right? How would you calculate the B part? How would you calculate the B part, the red part? It's PB directly, all right? And as you can see, the probability of A given B, the formula that you have learned, that you have memorized also works here, but we have tried calculating the probability by first principles as well. What is the first principle? While conditioning, the sample space is reduced, and in the updated sample space, we look for our favorable outcomes and we look for total outcomes. Give me a heads up if now conditional probability is crystal clear. I am very hopeful now it should be clear. I am not sure if I can put more efforts, but I am hopeful now it's very clear. Perfect, guys. Perfect. All right. So let's then move to next question. I wanted to do one more question, which is what created some confusion. But as Sri Ramya suggested, maybe we can do towards the end of the class that example. All right. So this is supposed to be actually a quiz. All right. But I don't think I have time to sort of launch a quiz and like wait for you. So let me just explain. You have a bag. All right. And you have 8 coins in that bag. All right. How much coins do you have? You have 8 coins. All right. And out of those 8 coins, you have 3 of them which are unfair. All right. 3 of them are unfair coins. 5 of them are actually fair coins. All right. So what do I know about fair coins? I know that the probability of getting a heads is what? Half. Probability of getting a tails is also half. All right. Now let's understand what is the case with our unfair coins. All right. Here I have been told that the probability of getting a heads is 0.6. All right. And the probability of getting a tails is 0.4. All right. Understood the question? Give me a thumbs up if you understand the question at least. Understood the question? Perfect. So you have total 8 coins, you have 3 unfair coins, and you have 5 fair coins. All right. So I'm saying that from this bag, you have this bag, right? You actually take out 1 coin. All right. So you have taken out only 1 coin. All right. It can be what? It can be unfair or it can be fair. All right. And this is actually the hint. It can be fair or it can be unfair. All right. And these unfair and fair are actually mutually exclusive even. All right. So if unfair has come out, then fair cannot come out. All right. And if fair has come out, then unfair cannot come out. Again, we are just taking out 1 coin, right? And they're mutually exclusive. Can there be a possibility? Can I actually take out a coin? And is it possible that it's both fair and unfair? Is it possible? No, correct? Do you intuitively understand what are disjoint sets now? All right. So these are disjoint cases. All right. Now I am using this coin. I basically flip it 2 times. All right. I'm flipping it first time or the second time. All right. I am flipping the same coin 2 times. First, tell me, if I flip this coin 2 times, will these events of flipping independent or dependent? Dependent on each other or independent of each other? Independent. Rashid had some problem. Rashid, if I have a coin, if I just flip it once, and if I flip it second time, will the probability of what will come on the second time dependent on what comes on the first time? Will it be dependent? No. All right. It will follow the general probability or general probability rules, right? Independent. So these 2 events will be independent. All right. So we've learned 2 things. First, either unfair coin will come out or a fair coin will come out, and these are mutually exclusive events, right? Because both cannot come out. All right. And second thing, the 2 tosses are independent of each other. All right. Now I want you to calculate what is the probability that I get heads in both the counts. All right. H comma H. All right. What is the probability that I get H in the first flip also, and what is the probability that I get H in the other flip also? All right, so I'm going to launch the quiz. All right, those who can do it, it's okay. Those who cannot, it's okay. We'll understand. We'll figure it out. So for this, I'm going to give you 2 minutes. I'm going to give you 2 minutes for this quiz. And the hint I have is that since these are mutually exclusive cases, you can just, how do you handle mutually exclusive cases? You do a PA plus PB, right? You total their probability. All right, you sum up their probability. This is the hint. We'll try to understand what I'm trying to say, but this is your hint if you want to solve. Don't worry, I have intentionally made these quizzes tougher so that those who are who know stuff already, they can also figure out if they know enough or not, or if they want to focus in the class or not. It's okay if you're not able to work it out. I've intentionally made these quizzes tougher. what do you have to calculate? You have to calculate probability that you get heads on both the tosses. Probability of 2 heads, yes. 18 seconds left, guys. I think we have a good percentage of people who have answered it correctly. Impressive, pretty impressive. I hope now this class made things clear. A lot of confusion that you guys had earlier. All right, I think the quiz has ended. I'm just waiting for the results to show up. So we have Rahul Shivani, Pawan Kumar, and Sriram who have won. And then other couple of folks that I can see, Ankit Gupta is at rank 4, Gautam, Rohit Sinha, Rajesh Yadav, Prateek Gupta, Akshar Nirvan, Dilreet. All of you guys have performed well. And by the way, I think I should probably start keeping prizes, although I'm not sure how many classes I'm left with to do all of this. All right, so let's try understanding this. But before we understand this, I actually want you to probably revise certain things and see, why this summary that I was mentioning of actually answers everything. All right, so first thing. All right, are we okay with the case where unfair coins comes up? Am I okay with this case that I am choosing an unfair coin? Am I okay with it? Tell me yes or no. Am I okay if unfair coin comes? All right. Am I okay if the fair coins come? Am I okay if the fair coin comes? All right. Am I okay if both unfair and fair coin comes? All right. Of course, this is not possible, right? This is a disjoint case. So this is not possible, right? But I am fine if either U comes or F comes, right? Either one of them comes, all right? So I have to add them, correct? I am okay with any one of them, right? And this is a mutually exclusive case. So which formula will we use? We'll use probability of A and probability of B, all right? Does this make sense that it fits in case 1 first? Getting a coin out of the bag. Does it make, is it clear that taking out the coin is this example? All right, perfect. So let me divide this event into 2 parts. I will calculate probability when, let's say, unfair coin comes up and when fair coin comes up. All right. These 2 cases, and I'll just add them, right? So, all right, what is the probability that unfair coin will come up? All right. How many unfair coins are present? 3. How many total coins are there? 8. What is the probability of a fair coin coming up? 5 divided by 8. Is this clear first? All right. So as for now, we've just taken out the coin and we are yet to toss them. All right. So I'll have to multiply it with 2 numbers, right? And why I'm multiplying 2 numbers directly? Because the next 2 coins will be independent, right? First thing, the toys, taking out a coin is independent of tossing the coin, and tossing these coins will be also independent, right? So these 3 things are independent, right? So I can just multiply them directly. All right. So what will be the case here? I am saying I want to know what is the probability of getting both heads. So what is the probability that I get a heads when I toss an unfair coin? It will be 6 by 10. All right. Probability of getting a heads will be 6 by 10, right? Because it's an unfair coin. Again, second time, the probability will also be 6 by 10, correct? Here, if it's a fair coin, the probability of getting a heads is 1 by 2, and the probability of getting a heads again is 1 by 2. And do you understand why we have used multiply here, right? Because taking out a coin, tossing it for the first time and tossing it for the second times are actually independent events, correct? They are independent. They won't actually influence each other's probability, right? As you can intuitively feel, right? And I have taken both of these cases. I have taken the unfair case and I've taken the fair case as well. All right. All right. So answer, just to tell you, the answer will be 29% or 0.29. If you just calculate this, it will be 29% or 0.29. Is this clear? Is this clear? Okay, many knows. Can you? Why 2 times? We're tossing this coin 2 times, right? We're tossing this 2 times. I mentioned it in the use case that we are tossing it 2 times, right? So first time, second time. Please, if in case somebody is not able to understand, please come on the stage and ask. It's very important that you understand this. And if you're able to understand these fundamental things, you would be anyway able to understand everything. And trust me, like, data scientists are not required to like solve all of this. I'm just trying to like do revise concepts so that you just somewhere know them. Prahlad, you'll have to ask me specifically what do you like, what did you not understand? I might not be able to get a lot of time to let's consider one case. So you can just, if you want to consider one case, so 3/8 into 6/10 plus 5/8 into 1/2. Sriramya, is it clear now? Is it clear? If all the coins were fair, the P would have been 25%. What does it mean? Since the 2 coins are unfair, the raise. Okay. Yeah. Makes sense. Can we multiply this answer with 2 for 2 heads? Yes, Shriramya. Yes. My laptop battery is running down. Oops. This will be problematic because I have a Mac M1 chip, and with one of them I've connected my iPad, and the other one I've connected my second screen where I've opened your chat. Oops. Okay, let's just finish this quickly. All right, let's just finish this very quickly. I'll then have to probably, if in case it's about to die, how much percentage it is? 10% still. I think we'll be able to manage. Otherwise, I'll probably just remove the second screen. I won't be able to see your chat, but I think that's okay. All right, perfect. So let's take another example. Let's do it very quickly. All right. So the question is, again, let's go back to casino. Remember, we were in the casino with our friend. All right. And we were playing some games. All right. So in this case, I'm not playing any game. I'm talking about casino machines. All right. So we have casino machines. All right. And these casino machines are actually sourced from 2 different sources, X and Y. All right. So there is factory X. All right. There is factory Y. And the casino machine, 60% of the times comes from factory X, and 40% of the times, of course, comes from factory Y. All right. Clear with the question? All right. So machines are coming both from factory X and factory Y, and there's a 60% chance it's coming from X, and the 40% chance it's coming from Y. All right. The next thing that I'm aware is that machines made in X works perfectly. Let me say perfectly by P. Perfectly 99% of the times. All right. Second thing I know is that machines made in Y works perfectly. All right. 95% of the times. All right. I'm just rushing through a bit. All right. I have less time, but you'd be able to understand. Nothing new in here. All right. So what events do we know here? All right. So let's put them as events. All right. So let me say event A, that the machine, let me say machine works perfectly. All right. Perfectly. This is my event A. All right. Let me say another event that I am interested in is that it's sourced from X. Event C, that it's sourced from Y. All right. These are the 2 events. We'll see what are we interested in. But do you understand these 3 events? If you're clear, give me a quick thumbs up and we'll just quickly go. All right. Perfect. Cool. All right. So I am interested in knowing what is the probability that it works perfectly. All right. PA is what? That the machine works perfectly. All right. I don't care if it is coming from X or if it is coming from Y, all I care is that the machine is working perfectly. All right. What is this example of? Which type of a question it is an example of? All right. We did 4 type of different examples, right? We did intersection, we did union, we did marginal, we did conditional. What is this example of? Very quickly, answer in the chat very quickly. What kind of probability is it? Is it union? I am interested in calculating probability of A. That's all. Marginal, correct. There are multiple events, but I'm just interested in knowing the probability of just one event, correct? All right, so let's just see what we did in marginal probability. One case is mutually exclusive. All right, of course, this is not going to be the case, this one, because there are dependent events, as we can clearly see. It's coming from X. Oh, sorry. It's actually coming from X or Y. So any machine can actually either come from X or Y. So it will be mutually exclusive. We'll talk about it. But we've done law of probability, law of total probability here. We'll discuss that in detail. All right. I just want to rush through this thing that we discuss law of total probability. So if you want to understand the concept, you can go back here and understand. But I'll just quickly cover what is the probability of what is the total probability that it works perfectly. All right, so let me also just write down what all do we know here. All right, so first thing, we know that P of A is what? P of A is 0.99. No, P of A is what we want to know. Sorry. First thing, we know that PB, what is what? That it's sourced from X is what? 0.6, right? Is that clear? Next, we know that probability of C is what? 0.4. Is there any doubts in here? Any doubts in here? Next thing I know is that probability of A given B. What does it mean? That probability that it works perfectly given that it's coming from B or it's coming from X, or is what? 0.99. All right. And probability of A that it works perfectly and it's coming from the other source, which is the Y source, right? It's the source C event, right? And this probability is what? 0.95. Are we clear with these 4 probabilities that we are given with these 4 probabilities? Are we clear? Rohit, what is your question? Did you say no to what? Can you quickly just raise your hand and ask me very quickly? All right, perfect. Cool. So we are already aware of these probabilities. So let's try to understand. Let's try to again maybe visualize this thing on the graph. All right, how will it look? All right. So first thing, tell me first thing. We have X event, we have X factory, and we have Y factory, right? And either a machine can come from the X factory or the Y factory, correct? Either the machine can come from X factory or Y factory. All right. So do you think these events will be disjoint or not disjoint? Will they be mutually exclusive or not mutually exclusive? Will they be mutually exclusive or not mutually exclusive? Mutually exclusive, right? They'll be disjoint, right? So a machine which is coming from X cannot come from Y as well. All right. So this is, let's say, event B, and this is event C. Remember, I have marked B as that it's sourced from X and C as that it's sourced from Y. All right. So this event represents B and this event represents C. All right. And also now let me talk about our favorable cases. So let me draw a green ball inside this, and let me also draw a green ball inside this, although these green balls will be much larger. All right. So what is this? What is this? This is 0.99 and this is what? 0.95. Do you understand this? Do you understand this part? Right? Although these values won't be 0.99, so I should not be marking them. I should be saying that this case represents that it works perfectly, and it comes from X, all right, and this works perfectly and comes from Y, right? But you do understand what I'm trying to say, right? All right. So did you notice? Did you notice here that as we discussed, since these are disjoint events, either a machine can come. If it's a perfect machine, we are interested in knowing what is the probability of a perfect machine, right? If it is perfect machine, either it can come from X or it can come from Y, correct? So the total probability that the machine works perfect, which is probability of A, can be divided into two parts. All right. First case, that it works perfectly and comes from what? Comes from X source, right? Which is the event B, plus probability that it works perfectly and it comes from C, right? And I can just add them. Why I can just add them? Because they are mutually exclusive events. Do you understand this part? Do you understand this part? That I can just add them. This thing P of A, which is it works perfectly, can be divided into two components. What are the components? This component and this component, correct? This green thing first, this first green thing is P A and B, all right? And this second green is P of A and C, right? Clear with this? All right. So now that you know conditional probability formula, can you actually also, let me write the conditional probability formula, by the way. A given B, PA given B can be also written as P of A and B divided by P of B, correct? Is that correct? So if I take this part here, I can say P of A given B, P of B equals to P of A and B, correct? So I'm just doing a little fast. I think you've done it multiple times. All right. So if this is clear, I can just replace this thing with P of A given B and PB here. And similarly, I can do P of A given C and P of C here. All right. So I'm saying that first case, the machine came from factory X, all right, which is the event B. And then now that I'm aware that it has come from the first factory, what is the probability that it works perfectly? All right. Because it's an dependent event, right? Second case, that it came from the second factory, right, which is the event C, right? And now that I'm aware that it has come from event C, what is the probability that it works perfectly? All right. And this is what we are interested in knowing, right? Does it make sense? Does it make sense? What is the question, Tulrose? Why is it not P of A given B and P of A given C? No, this is there, right? But you will have to multiply this part, right? You'll have to multiply this part, right? Are we asking to calculate conditional probability? No. We are saying that A can actually occur in two ways, right? So let me try explaining this with a tree. All right. So let me say that either it comes from factory B or factory C or factory X or factory Y, which are events B or C. All right. So it will be mutually exclusive, right? One of it is possible. And if it comes from B, either it will work or either it won't work. Here also, either it will work or not work, right? And here I'm interested in the case where it works, but it was sourced from B, and it works, but it was sourced from C, right? And this will be commas, right? So how do you calculate P of A and B? You calculate P of A and B by saying that, okay, it was sourced from B, so P of B multiplied by probability of A given by B. So Rose, is it clear now? Try understanding that we are not trying to ask the question which is conditional. I'm not saying that I've told you that it's coming from factory B or factory C. I'm saying that, I'm just interested in knowing if it works perfectly or not, but I've tried dividing it into two possibilities, two mutually exclusive possibilities. Let's say in first case, it came from factory X. Second case, it came from factory Y. All right, and I can just sum them together, right? Cool. So if this is clear, let me just hurry a bit, but you have the answer. This is 0.99. This is PB 0.6. Then you have 0.95 in here, and you have 0.4 in here. All right, and this will be the final answer. Any doubts? Any doubts in here? The answer will be 0.974. Any doubts in here? Give me a thumbs up if it is clear. And this is also again called law of total probability. So when I want to just calculate marginal probability, I am dividing it into multiple cases. I am just I'm just dividing it into multiple cases, and I'm just adding those cases together. All constituents of B, all constituents of, sorry, not B, all constituents of A, right? It's working perfectly here or working perfectly here. So these are separate cases. I can just add them together, right? Because if this is the case, it cannot be sourced from the other case, right? They are mutually exclusive. Try to understand this intuitively. Clear, guys? Shall we move to the next part? I think for last part of today's class. Right. I don't care. I mean, Vinay, the question is, I don't care if it's sourced from B or C. I just want to know what is the total probability that it works perfectly. All right. So I'll have to consider two cases, both the cases, right? If it's coming from X, this is the probability. If it is coming from Y, this is the probability, and this will be the total probability, right? And if you can actually see, if you try to interpret this, although this is not related to, let's say, probability, but you can think of it as that, these are the percentages. These are two percentages, and these percentages are actually multiplied by their weights. All right. So there are 0.6% chances that it's coming from first factory. So it will be given more weight, right? This 0.99% will be given more weightage, right? And if it is coming from second, it has lesser weightage, which is what? 0.4. So we've multiplied this percentage with 0.4, right? And this basically shows a weighted average of what? These two possibilities, two percentages, 0.99 and 0.95. I don't know if this will work. If it doesn't work for you, if you don't understand what I said in the last 2 minutes, it's okay. But if it worked for you, that's also good. Don't worry if you don't understand this part. But here I'm just doing, I would say, weighted average of two percentages. And of course, the chances from where it is coming will be given a bigger weight, right? 0.6 weight. And here it's giving, we're giving a lesser weight to this percentage. And that's why the final percentage accuracy of working perfectly is coming out somewhere in between 0.974. But still a little towards 0.99, close to 0.9, right? Because there'll be more machines which are coming from factory X, correct? Intuitively, if you have to understand this. Otherwise, you can just understand probability, and we'll do other things in data science. Don't worry. All right, so if this is clear, I'm gonna move to the very last part of today's class, which is Bayes theorem. And honestly, this is the only part which is required in data science. So all of this we've done, all of this practice that you've done is just to recall all your concepts, and further on you won't be required to do all these questions in data science. But it's a good idea to understand all of these concepts to understand the Bayes theorem properly. All right. Now imagine that again you are in a casino, and you are a casino owner, or maybe you, let's say, are a data scientist working for the casino. All right, data scientist can work for casino. Casino is all about statistics and probability. All right, so as a casino owner or data scientist working at casino, you realize that some people are actually standing around the game a lot, and they're actually counting. What are they doing? They're Hey guys, hello. 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 Can you guys hear me? Okay. And can you see me? Because I cannot.